thank all of you for coming up here. It's really been a wonderful experience for me so far, and also thank you for all of your help in keeping things going. It's been great, and I hope we continue to enjoy ourselves and enjoy the space. My talk today is basically a big question mark. I'm a thermodynamics guy, so I'm working thermodynamics into my viewpoint on agency. I feel like, similar to Kyle, I've done a lot of my work on Maxwell's demon, which is so the quintessential physical agent. So while I may not talk about Maxwell's demon in exhausting detail here, it's an inspiration for my viewpoint on agency. So I'm going to start with the question: is a particle an agent? So what are some things that make a thing an agent? Well, you could have perceptions or inputs. You could have actions or outputs. You can have memory. You can have intentions or goals, things that you're trying to optimize through your behavior. Well, let's just go through this. Can we eliminate the possibility of a particle being an agent? Well, I would say that the forces that influence a particle are a lot like its inputs, the things that it receives from the environment that tell it how to behave. And then it has actions. Does it have outputs? Well, by Newton's third law, equal and opposite reaction, just as that particle is influenced by its world, so does it influence its world. What about memory? Well, yes, it has position and it has momentum, and that is affected by past inputs and outputs. So far, it seems pretty agentic to me. But goals, how could a particle have a goal? It seems like an absurd thing for a particle to have. What does a particle want? Oh, exactly. You want to minimize the action. All of Hamiltonian mechanics has the goal of minimizing the action. If you wanted to think about thermodynamic systems, maybe it has the goal of maximizing the entropy. But you can frame a lot of physical systems as if it's an agent. You can anthropomorphize these things. If you choose, you can make a narrative that is rather agentic.
One thing I'm noticing here is that expression for, I guess, the Lagrangian does depend on everything else in the environment, so maybe that's one way in which the goal isn't contained within the particle.
That's the only problem you found.
That's the only problem. I will say, sure. I'm going to re-emphasize that it's a big question mark. My point of view
also,
here.
it's not even a fair thing to say because, I can't really have goals except for
the context. Yeah.
I just wanted to riff off that. I think that this makes it very salient how, I don't know, I'm sort of I'm inclined to be well, agency is maybe not a property of the system in isolation, but the environment has to be part of that equation. And then maybe there's some degrees in which how isolated my goals are from the environment, but there's really not.
I like where you're going. I'm not going to go in that direction this time, but I like that direction. And I think what I propose here will give us some insight into how to make that delineation.
Just as another point, I'm not sure the difference between the inputs and the outputs in this case.
It's the forces that influence the motion versus the forces that the particle applies to the system that influences its environment. It's like equal and opposite reaction.
But I guess what I'm saying is here the outputs are kind of exactly the same as the inputs really all the time in a way.
In a way, yeah. I think there's a symmetry to closed systems in that way.
Yeah. I just wonder how important that is in agency and a way to kind of collapse many inputs into a single output.
But I guess if the thing that's being acted on is sufficiently different, it's lighter or whatever, then it's going to be affected by the same. Maybe the fact that the forces are back to back is sort of forces are constructed so they have that property, but the influence you're going to have is different. So, if you have a bus hitting and it's off the top, if a bus is hitting a scooter, they're gonna have different effects on each other, even though you can design it so that the forces are equal and opposite. The effects aren't. So.
I mean, I think for equal and opposite to be violated, you have to have something like dissipation, entropy production, irreversibility. I mean, that is my intuition as a thermodynamicist. How exactly that manifests, I can't clearly state at the moment. So, is everything an agent by this set of rules? I don't really know. Well, I shouldn't maybe give away my full viewpoints, but I'm going to say that maybe it's not so much about whether something is or isn't an agent. Maybe it's about creating a measure of agency, rather than saying, okay, we have an agentic narrative for the system or not. It's everything as an agentic narrative, but is it simpler to reliably model that entity as an agent? Then is it simpler than, say, a mechanistic explanation? So, for instance, I think with a particle, while the minimizing the action of the Lagrangian is a beautiful insight, it's not necessarily giving you any simpler representation for what's happening with the particle. It's maybe easier to just say, okay, I know forces, I know fluxes, I know how this system behaves, and so therefore the mechanistic model is simpler. It's not very agentic. I'm not saying it's not an agent, but it doesn't have a lot of agency. Now, for something that we might think is an agent, I don't know if everybody's going to agree with me, but I was thinking about how babies, it's hard to predict their behavior until you figure it out what they want. They're like crying. You're like, do you want your diaper changed? Do you want to be rocked? Do you want a bottle? Afterwards, you're like, it was the bottle, So you have this goal-driven viewpoint of the baby, and that really simplifies your way of understanding its behavior. Whereas if you create a mechanistic model of a baby that is just an automaton, maybe governed by Hamilton's equations of motion, it's going to be really complicated to model this baby. So we would say maybe it's very agentic. We give it this more agentic status. We give them this more agentic status. Sorry, I think babies are people, for the record. For the record. But how do we measure agency? Well, I am an information thermodynamicist, so I will think about it through an information thermodynamics lens. And when I think about information theory, information thermodynamics, I think a lot about the mutual information between the past and the future. So on the vertical axis, we have the information shared between the agent and its future, horizontal, the agent and its past. And let's just put a particle on there. Well, a particle pretty much shares very little information with its past or future, but because it's deterministically evolving in a closed system, its future is entirely determined by its current state, as is its past. So it's the same. It's small, but the same. It's information shared between past and future. The same is true for any closed system. We could take the whole universe, and the information the universe shares with its future and its past is enormous. It is probably the largest quantity of information we could conceive of. But it's the same, past and future. And I would argue the universe as a whole, it's not easy to think of it as an agent. You could be like, the mind of God or something like that, but I'm not really here to advocate for that. I'll say the universe, when considered through its unitary evolution, is inert. Then you might consider something where its agency has been taken away. Say, for instance, a prisoner. A prisoner has a past. That past has led them to their current conditions of life, their state of mind. But by putting someone in prison, we limit their capacity to influence their own future. We limit their ability to act on their ideas, to enact plans to fruition, and then to continue with this politically motivated framework, on the other end, we have a dictator. This is Charlie Chaplin, by the way. Nobody that you should be offended by, I don't think.
Well, have you looked into that guy's life?
Maybe I spoke too soon. Hopefully less offended by him than the alternatives, I would say. A dictator seems kind of arbitrary when you're trying to predict them. They just do random stuff. What's to you seems random, and your life is chaotic and it sucks. The dictator is able to just say things and they become reality. They become the future. It's a really obnoxious type of agent, but one I would say is very high in agency. So to back off from the politically motivated, or maybe not so far from the politically motivated side of things, then you have current day AI, LLMs. Where are they in this this map? I don't really have the strongest argument for this, except to say that LLMs are built on transformers. Transformers are about taking functions of the past and mapping them to future predictions. And because they are, really, really effective at taking the whole of human knowledge, I would say they have a lot of information about the past. Maybe they're less effective at creating information in the future, we'll see. So far, experiments with LLM agents are not going so well. So I would say on the less agentic side.
Yeah.
What? Depends on what. LLM agents don't seem to effectively execute tasks. Yeah. So far, they're not. Especially over long horizons. And maybe the thing that we worry about is, or some people are rushing to create, is this AI super agent, which has a lot of information about the past, but largely what it's doing is creating a new reality for itself and for us. So, I don't know, what should we strive? Where should we strive to be in this picture? I mean, I don't want to be here. I don't know if I want to be here, but I also don't know if I want to be here. Well, I guess it's really up to you.
But you're not
where
really
you
committing
wanna
to
be.
you're not really committing to all these relations that, I don't know, the dictator has less information about the future than or are you committing to all of these placements?
Am I committing, like hard committing?
I don't know. The LLMs have more information than the. I mean, there's not a scale here. It's kind of a caricature, right?
It's
trying
a
to-
caricature. I mean, I don't have the statistics on dictator behavior or AI super agent behavior.
You are running this conference.
I'm going
yeah.
off vibes. This is kind of a vibey conference. I want to re-emphasize, this presentation is a big question mark. There are, I would say I've given you sort of a narrative for where you fall in these different areas, but maybe there's you could make counter arguments.
Can I comment on this?
Yeah.
The AI, the current AI agent thing, because having used a decent amount of the coding AI agents, they're very effective at accomplishing tasks. But I think that maybe the distinction is that they're, at the core, they do have large language models, but then they've been equipped with a bunch of tools designed by people that give them arms to affect things.
Right.
So there is I don't know, the AI super agent is some kind of combination of this plus tools to affect things, which I think is.
Well, I think there's tools, and that certainly expands your ability to affect the future, but I'd also like to argue that the very architecture of the way that you think and the way that your actions and inputs are related to your mind is an important factor. Obviously, if your outputs don't have any capacity to affect your environment, that's going to place you, somewhere over here, right? But, yeah. Sorry, Mara?
There's a way of thinking about this graph, which is a bit like, how far in the future can you reach? like, are you an agent that can reach far into the future or like not at all? And then so you then get a notion of like what's sort of the like cognitive horizon or the sort of time horizon into the future in which you can like project your goals. And I think, I mean, this is just like a bit of a data point, like on the LLM side, one interesting statistic or sort of scaling law that we have at the moment, and obviously, you know, you never know how long these things hold up, but currently the doubling time of like, the length of a software engineering task that an AI system can do autonomously is doubling every 4 months. So from like 1 hour to 2 hours.
Right.
So.
But I wonder if that improvement is also moving it further in this direction. Like maybe the improvement that we're seeing in agency is not necessarily reorganizing the architecture such that it's more oriented towards effectively using its memory to create some output. Maybe it's more about just like you're just moving along this general memory axis.
But I mean, so are you saying, okay, but so we're maybe training LLMs on more and more past data, and given that it sort of moves into that direction as well.
Yeah.
But then I'm like, do I really care? Like, if it ends up being able to like execute year-long plans.
Well, I think complexity is important. I think there are certain issues with, okay, we say, we could execute a year-long plan. I think of like, okay, we're predicting the future of the weather, right? We predict it further and further and further. But the reality is it's a chaotic system, so the amount of detail and the amount of compute that we need to put into extending that window it diverges. Whereas
you start geoengineering and then you get better at just making the weather be what you want it to be, right? Like that's kind of how you bring down.
No, it's inherently unstable. So that compute resources grow exponentially with the prediction and control.
But
There's no way.
nor saying you seed the weather. Like if you control the weather, you change the system.
The weather is a bit of a tricky example here, but I think you can like,
I'm just saying if it's chaotic, then you have to work with these instabilities.
There's something
resources grow
balanced.
exponentially with the degree of control.
I think this is an interesting area of exploration. I agree that having the idea of weather seeding is like expanding your tool set, right? And I think that might be, a way of, changing sort of the curve that you're following here, right? But that said, maybe that's not exactly what I want to get at here. I want to think more about how the dynamics of this memory interacts with past and future more generally. So, how do we wind up placing something on this graph? How do we have a framework for this? Well, for this, I think the most natural viewpoint is, you take random variables and you do information measures over them. And what are those random variables? Well, I would break it into, if you have something that you're investigating its agency, you break it into its memory variables, its input variables, its output variables, and then the memory variables of its environment. And this is representing a circuit, basically, of this interleaving feedback loop, which is quite general. And using this framework, you can start to look at what is the relationship between this random variable, or say this random variable, and its past and its future.
Okay, this is a great way to look at processes unraveling time, but your title says loops, and I don't see a loop anywhere here.
There's a loop. So
no, it's not drawn here, and that's really important. Inside your blue boxes and inside your transponders, you're going to have feed-forward networks. And my point, and I'll shut up because I probably am saying it, you need to have feedback so you actually can represent time properly. If you just constantly unroll your loops,
right.
Okay.
So Jim, this is unrolled in time.
I know.
Any feedback process you can unroll in time, and then it becomes a feed-forward process. I realize that this is, this suggests feed-forward, but there is a loop implicit in the fact that you're unrolling in time.
Implicit. You need to make it explicit for the system architecture sometime.
That
actually be dynamics.
These are dynamics.
No, that's a process. You run over it.
anyways, you can take,
It's a really deep point. Agent in time, we're using these concepts, and you're implicitly assuming that we understand that there's a loop, that the memory gets fed back to itself, and so far you haven't shown that.
I see a loop on the bottom right.
Finally,
in any case, you can, if you want a different picture for the loop, take a different picture for the loop. These are the pictures that I use for the loop.
good.
Okay.
Love those.
So,
love those.
now,
Satisfying.
we have one piece of the perception action loop, which is the agent. We can separate that out as a circuit. And we can view it a number of different ways. You can view it in this circuit viewpoint. You can view it through this network of random variables and their influences amongst each other. And then you can also view it as a probabilistic mapping from memory states inputs to the next memory state and next output. And this has sort of an automata representation. So, it also has a linear operator. Now, what do we do with this? Well, this tells us, or this gives us a way to analyze or understand the fact that there are many different presentations that produce the same process. So when I'm talking about a process, I'm really talking about an input-output process. So we have here a conditional probability. You have your output sequence and your input sequence. And this fully describes an agent's behavior from the framework of this perception action loop, this feedback cycle. Now, viewed on its own, it can be seen as, basically a circuit in the time in the following way, where you have sort of causal influence in this direction. The presentation includes the random variables for the memory. So there's the process and the presentation. Now, what is the presentation giving you? This is giving you like symbol probabilities. This is sort of agnostic to the inner world of the agent. And then you have the presentation. So this is the golden mean. And then this is a presentation for the golden mean that uses two states and a continuous parameter z, where you can sort of change the relationship between the memory variables and the output process while keeping the output process fixed. So this is basically illustrating that even for the golden mean, we have a continuum of two-state models that produce it. So what then do we interact with? Which is important? Which tells us about agency? I guess I personally just want to examine some of the different types of presentations of agents in order to better understand them. So there are predictive agents, and these agents are basically those that obey unit polarity, where the dynamics are deterministic when you're viewing them from past to future. So basically, the causal states update as a function of the observables. Whether you're in a transducer or a hidden Markov model, you have these steady updates. And from this, you get ideas of complexity. And now we can start to talk about Occam's razor. We can talk about, okay, this is the minimal complexity, the minimum function of the past that we need to predict the future. So the simplest causal narrative from past to future is accessible from thinking about these hidden states. And we know some things about this. For instance, we know that when you have sort of randomly selected HMMs, you often get these fractal mixed states where you have uncountably infinite distinct causal states. And the Simplex Astera team has been doing a lot of work to understand how these are embedded in AI, and they're finding that they are embedded in the residual streams of many different AIs in a variety of different ways. So these are useful. Well, why would we care about prediction? as a thermodynamicist, there are specific types of circuits that lead you to believe about or lean into prediction. So if you were to take a series of inputs, x, 0, 1, 2, 3, and your task was to just randomize it, that input. You're just taking inputs and you're not doing anything. You're not creating structure in your world. You're just trying to harvest energy. Then the constraint of zero entropy production basically guarantees that the memory contains all the information in the past that's relevant to the future. So it must be a predictor. The memory here must predict the process. Its information with the past must exceed the statistical complexity of that process. And this leads you to ideas about predictive machine learning. It leads you to ideas it leads you to understanding of overfitting in a thermodynamic context. So it seems to be a promising starting point to say, okay, from a thermodynamic point of view, you want to minimize entropy production. Well, what about retrodiction? There's a different physical setup. There's a different physical setup from harvesting energy from a pattern. You could instead try to create patterns in the world. Maybe this is something agents do more actively, is rather than just harvest energy or try to predict something, they're actually trying to create something useful for us to interact with. So if we're creating a pattern from randomness, we get a different relationship. We see that when the entropy production is 0, that you actually want to be retrodictive, that your memory wants to capture all information about the future that's relevant to the past. So why retrodiction? Going back to this model of the golden mean, we see that basically if we shift from a predictive model to a retrodictive model, the entropy production starts at a high value and decreases to a lower value for the retrodictive model. Yeah.
In the last slide, you were talking about prediction and retrodiction of different things. So prediction of input and retrodiction of output.
Yeah.
So here, when you're saying going from prediction to retrodiction, it's not clear to me if you're talking about input or output.
It's outputs in this case. So if you're predicting your outputs, it's wasting energy. Yeah. So then one of the things that I've been trying to understand better is what retrodiction looks like in AI agents. Is a retrocausal state an informationally efficient plan? The most general retrocausal state is one where you take every possible future outcome and you make that your memory state, and then you just randomly choose between those memory states. So you've chosen a specific future, and then you roll the dice at the beginning, and then you create that future. So it's like you have a plan. You have some planned outcome. These sorts of states have sort of a co-unifilar condition where the past state is determined by the future and the observables, and you have a similar measure of retrodictive complexity. And I think that this retrodictive mixed state might have AI safety implications. For instance, it could tell you, okay, if you look at a possible catastrophic outcome, it might tell you, you're in this belief space, and that might be a danger zone, and you might have a region that corresponds to positive outcomes. Yeah.
Can you say what I didn't quite get what you mean there?
So this is a belief state in your machine that corresponds to a retrodictive state, a plan that yields a particular outcome, a bad outcome, and this one a good outcome. Yes. So I realize I'm running short on time, so I'm just going to propose that causal irreversibility might be a good measure for agents that we want to test. And we can see that it can be pretty extreme sometimes. You can have a fractal set of retrodictive states and discrete predictive states. in which case you have infinite causal irreversibility. And you can flip this around too. You can also make something with simple retrodictive states and very complex predictive belief states. And I have an intuition, again, this is a question mark, for what these different types of behaviors mean. There's, the case where you have a simple description going forward in time and a complex description going in reverse time. This to me calls out a lot of physical processes like a shattering glass, where shards scatter out over the floor in sort of an intuitive way that's easily simulated, but the reverse process would be very complex to simulate. Yeah?
I'm wondering, natural language as a stochastic process, where it fits on this,
Natural language, it seems, has some causal irreversibility. It's harder to predict in reverse time. Paul had shown me a paper on this. But it depends on the language a little bit. French, I think, is more causally reversible.
Okay, more
Yeah.
agent.
Yeah, I guess more agentic.
They think so. Yeah.
What would be something that has a retrodictive bias? Well, maybe these AI super agents are using memory efficiently so that they're very hard to predict, but they create a lot of structure in a way that is only using, using their memory resources in an efficient way. And so, coming back to this information theory for agency picture, where might my predictively biased and retrodictively biased processes lie? Well, process A is predictively biased, meaning that there's one presentation, the minimal retrodictor. Oh shoot! This is is this flipped? No, the information with the past. Minimal. Sorry, I think I got these switched up. Okay, I'm gonna need to think about this. But the idea is that maybe the processes themselves don't have a distinct location on this map, but are more represented through this larger dimensional object in this map. And sort of depending on these objects are bounded by the informational properties of different presentations. And maybe the space of presentations tells us something about the process itself. So with that, I want to propose a more nuanced language for agency. There's maybe something like presentational agency, informational relationships between the agent's mind, past, and future. This is something we can actually talk about in this context. There's process agency. There are informational bounds on the relationship between the agent's mind, past, and future. So bounds rather than explicit relationships. And then back to something you said, Nora, is about context. There's context-free agency, which says, which asks sort of what are these informational relationships independent of the input process. And then there's contextual agency, where you look at the joint process when you're driven either by a particular input process or by a feedback mechanism, and then you evaluate the informational relationships there. What an agent is, I still don't know. This is a question. Is it everything? Is it just a few things? Well, with that, I'd like to thank Fernando Rosas, who worked with me on a lot of these projects, and then Paul Reichers for his work with BITS. And I'd also like to thank all of you for coming here and really making this a special event. It's been a lot of fun so far, and I hope we can continue.
So Alec, do you think a particle is like predicting and retrodicting?
A particle, I think, is simultaneously doing both because it's Markovian.
That's Laplace.
Yeah.
It's on the same axis as the whole universe.
Yeah, it's on the same axis as the whole universe. Yeah.
And also, so I guess that all the